In the realm of cutting-edge AI technologies that demand unparalleled data processing and computational power, choosing the right networking infrastructure is more critical than ever. Additionally, as businesses and researchers push the boundaries of computational performance, the choice of network fabric becomes pivotal in balancing efficiency, scalability, and cost. The networks we design and implement directly impact system performance and business outcomes, from the scalability of data center infrastructure to the cost efficiency of operations. Ethernet and InfiniBand are the two dominant players in this arena. Each brings unique strengths and trade-offs, leaving organizations with critical decisions to make when designing and optimizing their high-performance networks. Welcome to today's webinar on optimizing high-performance networks, Ethernet versus InfiniBand and beyond. In this webinar, we'll explore these considerations and examine key factors influencing network performance. From understanding the nuances of Ethernet and InfiniBand in high-performance environments to evaluating the necessity of fully non-blocking fabrics and the role of lossless networking, we'll provide actionable insights to guide your network architecture strategies. Joining me today is an expert, David Barman, Director of Technical Marketing Engineering, who spearheads Juniper's Ops4AI lab and is speaking with businesses and researchers almost daily. David, it's a pleasure to have you on this webinar. I look forward to learning from you and uncovering the performance and nuances of Ethernet versus InfiniBand in modern AI data centers. Can you please introduce yourself and help us demystify these complex topics?
I'm David Barman, and I'm an engineer on the data center product team. I'm going to be talking about our Ops4AI lab. I spend most of my days in the lab running AI training models, trying to discover the best architecture and tunings to get the most performance out of AI training. This is a diagram of the Ops4AI lab, but before I get into the diagram itself, I wanted to answer the question of why to build a lab. So when we first started on our AI journey, InfiniBand really was the primary networking technology for AI networks. And this is because InfiniBand was used for HPC, high performance computing. And when GPUs started being used for AI networking, the InfiniBand just followed along with it. But at Juniper, we wanted to prove that Ethernet works for AI networking and that it would be a viable technology and competitive with InfiniBand. So we built out several clusters of NVIDIA GPU servers. So we have a cluster of 8 A100 servers, 4 H100 servers, and 4 AMD MI300 servers. And we use these clusters to bring customers in and show them how well Ethernet works for training. And this was highly successful and led to some important wins. But beyond just proving that Ethernet is viable, the lab has evolved into allowing us to understand the entire ecosystem, understand what our customers experience when bringing up AI networks, and allows us to provide good tuning and architecture recommendations for customers and even some partners that are also providing equipment for AI networking. So in the lab, we've got various networks that as a whole make up the entire fabric. So we've got a front-end network, and the front-end network is really the thing that kind of manage the entire lab. So We've got servers that provide orchestration for running jobs. Now, in our case, this is Slurm, but this could be Kubernetes, OpenShift, Run AI. There's a lot of different options there. The front end also provides what I'll say is low-speed storage. It's NFS mounts to the training servers where the scripts used to start off the jobs are shared between the servers. It also provides management, logging, telemetry, things like that. So we have the backend network, or I should say networks. There's a separate backend network for each one of the clusters. And the backend networks, I really like to, I say this is the star of the show. This is where the real magic happens. Because so much data is transferred between GPU nodes during a training run, you need a very high speed, high performance, low latency, low loss network. And so these are typically generally Tomahawk class switches. And uh, these are 200 gig Ethernet or 400 gig Ethernet between the compute nodes and their respective leafs. And it will be, depending on the cluster, either 400 gig or 800 gig Ethernet between leaf and spine. And one interesting aspect is that we can swap out the spine through just software configuration between a shallow buffer, say QFX switch, or a deep buffer PTX switch, depending on what sort of experiment we happen to be running. We also have the final network as part of this, which is the dedicated high-performance storage backend. This is a set of leaf and spine switches that connect the compute nodes to high-speed storage. Now in our lab, we've got Weka high-speed storage and VAST storage. I don't have VAST shown on this diagram. This is brand new for us. So we're always trying new technologies, bringing things in to see what works well in the lab. The high-speed storage that is really dedicated for the use of training. And this is when things like checkpoints during a long training run will store the state of the model for replay if something goes wrong during a training run, hardware failure, for example. And it also stores the models themselves, so container images and things like that. So in the lab, this is really we call it a design resource because we're always doing experiments in there to determine what the impact of changing one parameter or one aspect of the architecture, what is the impact of that on job completion time? And job completion time is the primary metric for AI training. So we don't have time to go through all of these, but this is just part of some of the things that we have either already investigated or that is on our roadmap for things that we would like to. So, what is the best load balancing strategy? What about DCQCN? Does VXLAN have any impact on job completion time? What about latency and buffer depth? I mean, the list goes on, and there are always things being added to this. I like to say that we follow the scientific method. We have this mental model of how training works, what goes on really under the hood, and then something will happen and we want to understand a little bit more. So we form this hypothesis, design an experiment, run the experiment, and then based on what we learn from the results of that experiment, we refine that mental model and just keep going in a cycle. And this has really helped us a lot over over time to really see what the best way to build out these networks and how that impacts various training models. So Ethernet versus InfiniBand. This is really the reason that we initially constructed the lab. And we felt that Ethernet would be a viable uh, alternative to InfiniBand, but we really needed to kind of prove that out. Now, it turns out that Ethernet absolutely is viable and in many ways is equal to or surpasses InfiniBand. And so with running an AI training model, you need to avoid congestion. Congestion will cause loss and degradation of performance. And so, InfiniBand has this uh, thing called subnet manager, which is a central control over uh, how data is routed through the fabric. And that because it's central control, it it doesn't scale that well. Whereas for congestion avoidance on Ethernet, we've got many different options. So load balancing with DLB, dynamic load balancing, GLB, global load balancing, Q-pair pinning. There's many other uh, alternatives for a distributed method of avoiding congestion. And then, in these networks, some amount of congestion or queue buildup is inevitable. And with an InfiniBand network, this is done on a request grant mechanism where the network allows the compute node to send its data. And this does very well, and InfiniBand is uh, completely lossless because of this mechanism. But it it doesn't it, it doesn't allow the bandwidth to be fully utilized as much as it could be, perhaps. And with Ethernet, we achieve lossless Ethernet through a mechanism called DCQCN. This is a combination of explicit congestion notification and priority flow control. So really the takeaway from this slide is that uh, the advantages that are seen with InfiniBand also have the same advantages with Ethernet. So InfiniBand really, from a congestion avoidance and control standpoint, doesn't have many advantages over Ethernet at all. One of the big things is where can you buy your InfiniBand equipment from? There's one supplier. You can only get it from NVIDIA, whereas Ethernet, there are many, many different options. And the Ethernet realm is very competitive. So the cost of running Ethernet is much lower. So in order to prove that Ethernet was viable, we said let's go ahead and do some tests. So ML Commons provides these ML perf benchmarks, and so we've run BERT large, DLRM, Llama 2, Llama 3, GPT. We've run all these different AI models in the lab, and we've even run proprietary models from customers. So one example here is BERT large. With BERT large, we ran on our 64 GPU cluster of our A100s, and we got a job completion time around 2.6 minutes or so. Well, ML Commons allows various organizations to publish their results. And so there's a number of InfiniBand results in there that are on the same exact 64 A100 GPUs. And those range from 2.5 to almost 3.5 minutes. So we can see that our training time is very competitive with InfiniBand. We also did Llama 2 using the NeMo framework model. Now, in our case, we only have 32 GPUs. We've got 4 H100 nodes, and each one has 8 GPUs, so 32 total. There isn't in ML Commons a 32 H100 GPU result, but in these, we generally see that the results scale linearly. So you would expect the performance of a 32 GPU network to take about twice as long as a 64 GPU network. It's not exactly linear, but it's pretty close. So we were getting 7.9 minutes on training versus 5.1. So you would expect on a 32 GPU cluster to get around 10 minutes or so. And so we're seeing a little bit under 8. So very competitive again there. So yeah, is the cost and operational complexity of InfiniBand worth it? We don't really see that it is. If you look at the largest AI clusters that are being built out, the largest ones are being built with Ethernet today. NVIDIA themselves have said that we're all in on Ethernet. They're providing Ethernet switches themselves. So you have to kind of wonder, is InfiniBand approaching the end of its life? Ethernet has really proven that it is viable and is the way forward for building large networks. Now, the total cost of ownership, there's no question. Ethernet is so much cheaper because of the fact that you can go to multiple suppliers. There's a good competitive ecosystem there, and studies have shown that the 3-year cost of ownership for InfiniBand is 122% higher. This isn't 22% higher, it's 122, so more than double the cost for Ethernet. And really, what we're hearing is that customers don't want to be locked into one vendor, and the fact is that finding the staff to run an InfiniBand network it's not easy. There's just so much of an explosion in growth of AI, and I think even NVIDIA doesn't want to have to go out and train all of these new engineers on InfiniBand. So yeah, being GPU agnostic with Ethernet. Ethernet will run on NVIDIA, AMD, other GPUs, and AI compute elements. So in our opinion, AI pretty much always wins. Okay, so we talked a bit earlier about DCQCN being the Ethernet mechanism that lossless networking is achieved. So I wanted to dig in a little bit more into that. So with Ethernet, you want to avoid congestion in the first place, and that is done with DLB, dynamic load balancing. And we've had other webinars where we've discussed this. But like I mentioned before, when you're transferring data at high speed among a network of GPU servers, you will inevitably build up some queues. And so DCQCN is the use of explicit congestion notification and priority flow control to deal with congestion before it gets really out of hand. And the way that this works is that as data is being transmitted across the fabric through the switches, if there's a queue that's building up, would be an output queue. If that builds up and gets beyond a configurable threshold, then the ECN bits in the IP header are set to a congestion experienced state. And so when the receiving NIC on a remote GPU node receives those ECN tagged packets, then what it does is generates what's called a CNP packet, a congestion notification protocol packet. And this is sent back to the source NIC. And what this does is it lets that NIC know that, hey, this particular flow saw congestion on the way to me, so you need to slow down somewhat. And it's this ECN feedback through CNP mechanism that allows each flow to adjust its rate to avoid congestion. And this works extremely well. There are still some cases, however, where even with ECN, that some queues could build up, and that's where PFC comes in. PFC is more of a hammer approach rather than, say, a scalpel. So what it does is when an input queue is building up on a switch, that switch will send a pause frame to its upstream neighbor, telling it to hold off sending packets to it so it can drain out its queues. And so between PFC and ECN, we can achieve 100% lossless Ethernet. Well, we wondered, do you have to have 100% lossless in order to achieve the best throughput? Well, we have a lab, so let's put this to the test. So we brought in a model of one of our customers. This is a custom model that they have. It's proprietary. This customer is in the financial sector, and they use this model, internally. And we brought it in, we ran it in two scenarios. The first scenario was not lossless. We only had ECN configured. We did not configure PFC. And so as expected, we saw a little bit of loss. And then on scenario 2, we configured the full DCQCN, full lossless Ethernet. And to our surprise, the job completion time increased when we went to a completely lossless network. Now, it's a common, I'll say, trope that any sort of loss in an RDMA network will cause the job to fail. You cannot have any loss. And that is absolutely not true. RDMA has loss recovery mechanisms. But we were surprised to see that even with a little bit of loss, those recovery mechanisms allowed the job to complete faster than with lossless. So we said, let's try another one. We use DLRM, and this is a recommender model. We ran it, same scenarios, ECN only in scenario 1, full lossless in scenario 2. And in this case, we saw a 22% improvement in job completion time. And so what this really tells us is that there is no one size fits all with some of these settings. It really depends on the model that you're running and your use case as to whether you need 100% lossless network. So yeah, you'll hear all the time that you need 100% lossless, but that does not always give you your best results. When you have a full lossless network, such as with DCQCN or with a request grant mechanism, you can get some global slowdowns in the fabric, and that leads to less than 100% utilization. And with that back off, you can actually hurt performance. So yeah, that was one of the surprising takeaways that we've gotten out of the lab. Yeah, another thing that we investigated is whether you really need a fully non-blocking fabric to get the best performance. So what a non-blocking fabric is it, it's a mechanism for architecting a network such that any node can talk to any other node on the network uh, without, at full speed. And so what we see in a non-blocking network is that the bandwidth from the compute nodes to their respective leafs is equal to the bandwidth from the leaf to the spine. And in this way, we can get full throughput across the fabric. Now, is it possible that you could configure the leaf spine bandwidth to be less than the leaf to node bandwidth? Could you do that? Well, of course you could. There's no reason that you couldn't do something like that. But the real question is, what would be the impact on training time? And so, you know, we've had people ask us about this, and the reason that they ask about it is that uh, they might want to save some money on optics, or lower their capex cost on switch ports and things like that. So we said, all right, let's test this. Put the same models to the test, DLRM, and the same customer model that we tested before. And with a non-blocking network on DLRM, we saw about 2.8 minutes of training time. And then we disabled half the links between leaf and spine, reran the model, and we were somewhat pleasantly surprised that, sure, the training time went up a little bit, but it didn't go up by much. It was still about 2.8 minutes. So uh, in this case, we ran the customer model, and we saw almost double the time when we went to an oversubscribed spine. And this is kind of, this was also a little bit surprising that we could get two completely opposite results. One is that, yeah, it doesn't matter if you're oversubscribed. And the other one is that, oh, it matters a whole lot that you're oversubscribed. So yeah, it comes down to, again, you really have to, understand your model and uh, know whether the really understand whether the whether your model can tolerate that oversubscription or not. Now, at Juniper, we recommend going with a full non-blocking architecture for a few reasons. One is that, if you're building out even a modest sized network, you're going to spend, tens or hundreds of millions of dollars. And, most of that is in the GPU compute nodes. The network itself is a relatively small amount of an AI cluster. And so, saving a little bit of capital by oversubscribing doesn't save that much in the big picture. And the other reason is that, as data scientists, as they operate, they will often change the model, and you'll find that small tweaks to a model can result in a large amount of, uh, maybe bandwidth across the network, and that a model that yesterday worked fine today is causing excessive congestion and poor performance. So, unless you really understand your model, we don't recommend trying to, oversubscribe a network and having to go back and, ask for more funding later because really cut corners on the architecture. So I think that's, yeah, my last slide there.
Thanks, David. These are great insights into the performance of Ethernet versus InfiniBand. Very informative. And my experience of over 2 decades in the industry tells me that Ethernet will win this battle too. And but before we close, David, I have a couple of questions that come up routinely as we talk to our customers and partners. And it's more like an FAQ, I would say. And I just want to pick your brain and maybe, take a couple minutes for you to answer those questions. Number one would be, how are you incorporating the new models into which is our Ops for AI lab?
Sure. I think I have a slide on that. Yeah, so in the lab, uh, most of our models come from ML Commons, and so we'll bring those models in. Um, but we also have models. A customer or partner might have their proprietary model, like the one I mentioned earlier. And
Mhm.
so, we'll bring those in. We prepare those, and generally, if they aren't already containerized, we'll spend a bit of time containerizing the model. We prefer that they're already containerized, but sometimes they're not.
Mhm.
And then, if there's generally with training, there's some data set that comes along with it. We load the data set onto our high performance storage, and then we'll generate the execution scripts that go along that allow us to start up that model and run it in with various parameters. And so usually when we're bringing a model in, it's because there's a customer that's got some thing they want to discover about either their own model or just some one of the standard models. And so we'll work with them to uh, try to understand what it is they want to learn. We'll put together a test plan with them, and then we invite them to work with us to execute those tests. And so what we'll generally do is we'll sit down. A lot of times it's a virtual experience. We'll, get onto a Zoom or Teams call and, we'll run the tests. And generally what they say is that, okay, I see how these go. Um, I see the first few tests and, I don't need to be on here for all of them. And so we'll trust you guys to go ahead and run the rest of them. And so we will generally run through the rest of the tests, collect up all the results, make some nice graphs, put it into a report, and then share the report with the customer. And uh, in every single case, I've never had a case where a customer was not thrilled to see the results of this. And generally they're usually early in their AI journey, and they appreciate the learning experience that they get from working with us. So yeah, and I've got a list of the standard models that we run. I think I mentioned a lot of these before. One that I didn't mention is there's uh, something called nickel tests, and this is a set of tests that uh, is run. Uh, you could run on your GPUs that uh, isn't really a training model, but it's more of a performance test kit, and we run these quite frequently. In fact, I run them probably more than I run AI models themselves because it really stresses the network and it allows me to see the impact of training or of tuning on the on the performance. So yeah, it's yeah.
Basically, the customers and partners are getting a white glove service from Juniper, right? As they bring in new models or they're looking to get results
That's
from the models. Perfect. And for listeners, you can actually sign up for or reserve your spot in the Ops4AI lab using the link below, and we welcome you to get started on this journey and reach out to us using the link below. All right, David. The other question I have for you is I read Juniper's blog about submitting results to ML Commons, and you actually alluded to in your presentation as well. Could you please share insights on our work with ML Commons?
Sure. Yeah, and I think I have a slide on that one. Um, yeah, so I guess I probably should describe what ML Commons is. They're really an organization. I want to say they're like almost 7 years old now, and it's an organization that is made up of um, a large group of members. I think it's over 100, maybe multiple hundreds of members, and they range from academia to startups to very large enterprises. And their goal is to help accelerate AI innovation, kind of leveling the playing field for AI and make it easy to get started in AI. And so they provide what's called ML Perf, and that's their AI training benchmark suite. And this is software that you can download, and it makes it really easy to run popular AI models and compare uh, results with others. So I've got here, these are the some of the ones. I've got some Juniper ones on there, but you can see ASUS and Supermicro on there as well. So they provide the containers, the software to run them, and to collect the performance. And so, depending on what your architecture is and your network, uh, that's all included in what gets collected. And they have this database where all the results go in there that people submit. And so, yeah, Juniper is one of those. We submit results on a periodic basis to ML Commons, and this is very useful uh, for those that are, say, setting up a new cluster. Uh, you have a brand new cluster, and you run something, and you see a result, and you just have your own result, and you think like, well, is this the performance that I should be getting? Like, how does this compare with someone else? Do I have things configured and tuned properly, or could I be getting better performance out of it? And so provides a way to compare your own results with what others have. So you can use it to maybe do sizing if you haven't acquired uh, your compute nodes yet. Uh, and I also like to think that maybe it kind of provides a sort of bragging rights in results. If your results are up there on the leaderboard, then yeah, I think there's a little bit of competitive nature to it. So yeah, I think it's a really good resource for the community.
Agree.
Mm,
Totally.
mm.
Um, the third and the last question, David, I have is if I look at the presentation on slide 18, I observe that there are two models, DLRM and the customer training model, produce different results for non-blocking and oversubscription. So what distinguishes these two models? If you can just throw some light there.
Sure. So what we find is that the amount of network bandwidth, the total data that is transferred by a model really depends on the model itself. It depends on, is this model doing like what sort of parallelism? If it's a strictly data parallel model, then it may not generate as much network traffic. Uh, Depending on other parallelism strategies and the type of model it is, some models generate a whole lot more network bandwidth, and other ones generate somewhat less. I mean, they all need to be networked, so they're all going to generate some amount of data. But yeah, some of them stress the network quite a bit more than other ones. And in this particular case, DLRM doesn't generate enough to cause uh, like long-term congestion and queue buildup on the fabric. Whereas the customer model, we had 400 gig links during these tests between leaf and spine, and this model was generating sustained rates at times of exceeding 350 gigabits per second on those links. And so, even though it's not running at a full 100%, when you look at like microbursting and things like that, it with the 2-to-1 oversubscription, it really slowed it down a lot. So yeah, that model really needed the capacity there. Other models, if you're not stressing the network enough to congest it with half your links disabled, then it's probably going to perform roughly the same as if you had your full non-blocking. So yeah, it's really boils down to uh, how much data it transfers across the network at what speed.
Fantastic. Thank you, David. Thank you for wonderful insights. And with this, we conclude our today's session. And thank you, viewers, for listening. We will have the recording of this webinar available for replay. Um, it should be available on juniper.net. So feel free to check it out. And with that, thank you to all the viewers.